Hello everyone. Today I will be explaining question 1 and question 4 in tutorial 3. We will start with question 1, and if you can see the question, it states that we have a thin electronic component, and once we read this electronic component, so we are talking about electricity being lost as a form of heat. Whenever electricity go through wires, we have some resistance, and this resistance result in some of the energy converted to heat. Anyway, this electrical component has a surface area of 950 centimeter square, and in order to cool this component, we have to provide a sink in which this heat generated will be transferred and will be pulled off from the electronic component. In this heat transfer, we face two kinds of resistance. The first one is the resistance in the interface between the electrical component and the sink, and the heat conductance is given to be 25,000. Another resistance will be that we have a convection and radiation after the interface, and the combination of convection and radiation is given to be 1.3 Kelvin per watt, and the heat transfer is 45 watts, and the surrounding temperature is 30 degrees Celsius. And the objective of this question is to find the temperature of the electronic component. Anyway, if we start with stating our assumption to solve this question. First of all, of course, we are talking about steady operation, no change with time. The temperature is linear. Temperature profile is linear, and the second assumption that heat transfer occur only in one direction, which is from the electrical component to the sink directly. Anyway, if we start with solving the problem, first of all, we need to convert the area from centimeter square to meter square. This later, so we can. It's a simplification to calculation later. Anyway, then if we check the general formula for the heat transfer, for the steady state, no heat generation, heat transfer, it will be that we have the heat transfer is equal to the temperature difference divided by the total resistance. In this particular question, the total resistance is equal to the resistance on the interface plus the resistance of the convection and radiation combination, which is given to be 1.3. So RT is R interface plus R radiation and convection. R interface formula is equal to 1 over HC, given the question to be 25,000 multiplied by the area, and this is plus R of the combination radiation and convection. Anyway, if we just write the equation and calculate it, we will notice that the total resistance is 1.30042 Kelvin per watt. After we found the total resistance, then we substitute again in our general formula to solve for delta T. So delta T is equal to the heat transfer rate multiplied by the total resistance. We do the math and we find that delta T is equal to 58.51 Kelvin or degree Celsius. Doesn't matter, we are talking about temperature difference, so it's the same. Kelvin and Celsius is the same. Anyway, finally, in order for us to calculate the temperature of the electrical component, the delta T is equal to the T of the component, which is the higher one, minus the T of the surrounding. So if we solve for T of the component, we will find that it's equal to the delta T plus T of the surrounding. And if we do the math, the final temperature of the electrical component will be 88.51 degrees Celsius. So for the second part of the question, it's explanation of does the contact resistance at the interface of electronic component play a significant role in the heat removal or not. And to answer this question, we need to refer to the total resistance. We will find that the resistance of the interface is only maybe 4.2 multiplied by 10 to the power of minus 5. And we can notice from that there is no significant value for the resistance for the heat in the interface. Therefore, there will be no obvious temperature difference in the interface. And yeah, the interface resistance will not play a significant role in the heat removal in this particular problem. So that's all for question 1.